All right, here we go. Welcome to class for Monday, April 6th. Today we're going to be talking about collisions. Specifically, we're going to be talking about how we can use momentum to talk about interactions between objects, which we will call collisions. I also thought this image was particularly appropriate. I don't know how many of you are feeling like this class is punching you in the face, but I feel like this class is punching me in the face, and I'm not even taking the class. So hopefully it's not quite as bad for you. All right, reminders. So the big thing to emphasize right now is keeping up. So things that you should do this week. So this week you should be working on the chapter 9 homework on Wiley Plus. That's talking about momentum. You should also be working on the chapter 9 adaptive practice, which is also focused around momentum. And the perusal reading that's due on Wednesday is talking about collisions. Just as a reminder, the perusal readings are not always due the same. They're not always due on Monday anymore. In order to make things work, they had to bump around a little bit. So this next one on collisions is due before class on Wednesday. So that's the deadline, 6 a.m. Wednesday morning. So have a look at that. Give it a read. It's not the longest thing, but it is pretty detailed. And so you should plan to spend a little bit of time on it. The other thing you should be working on this week is video experiment number 3. That's the Newton's Cradle video experiment. And number 4 will be posted on Wednesday. So that'll also be one to start working on. Okay, so that's course things. Any questions about any of this? All right, and then as a reminder, I don't have it on the slide, but I am doing office hours immediately after class, Monday, Wednesday, Friday. So if you have questions on the Wiley Plus homework, the adaptive practice, the perusal reading, the video experiments, any of that, you can catch me right after class. Sean, our Fearless LA, is also doing office hours Mondays and Thursdays from 11 a.m. to 1 p.m. And just as a reminder, you need to email Sean before you try to get into the Zoom room, just because it's the Zoom room will automatically shut itself down if it's inactive for a certain period of time. So Sean may or may not be there. But if you shoot him an email between those times, he'll be able to jump on, and then you guys can chat and work through things.
Dr. Nelson, I figured out, because I am doing my Zoom meetings using the class link, apparently it won't sign me out.
Okay.
As long as I keep the webcam open, then, like, last time or on Thursday, I was able to hold office hours the entire time, and it worked.
Great. Okay. So yeah, we'll that makes things a little bit easier. So that's Mondays and Thursdays, 11 a.m. to 1 p.m. Okay. And then I'll just add in, just on a personal note. I know everybody is probably feeling a little overwhelmed with various things at the moment. I know I am. I used to use this analogy to talk about algebra-based physics, but I think it works better for online. Learning physics online is kind of like pounding a nail in with a rock. It's technically possible. It is not efficient. It is messy and frustrating. But that's the tool we have at the moment. So we're going to try to make the best of it. But we just sort of have to build in some expectation that it's going to be inefficient, messy, and frustrating. But survivable. That's the other key point I want to make. We're all going to make it through this. It's not going to wipe us out. So Okay. Oh, actually, I'm going to hold off on that one. I'm putting
Dr.
together.
Nelson,
Yep.
do you think that this is just like a sidetrack, but do you think next semester for Physics 204B, we're going to be doing the same thing online?
That is a $1 million question. At the
Because
moment,
this is already so hard. I can only imagine how Physics 204B is going to be.
so I can tell you, I can only tell you what I have heard. Nothing. I have heard nothing official about fall, but the university is beginning some what they're calling preparations in case it becomes in case it is they are unable to reopen campus. And so it's not clear what's going to happen with that. On top of that, the physics department has an added complication that we are supposed to be moving into a new building, and construction on that building was halted as of Friday, supposedly for only 2 weeks, but I don't really believe that. And I'm not sure anybody else does either. So even if the rest of the university is back on campus, physics may not have a building to be in. So anyway, I have no idea. I don't even know what's going to happen in 10 minutes very often. So I have no idea what's going to happen next semester. I really, really hope that campus is able to reopen on some level, because while there are some classes, you know, like if you're in a 100-person like intro sociology class or something, I think moving that online probably wasn't catastrophic. But I am really hopeful that some of the, you know, the natural sciences and engineering disciplines, and you could also imagine this for some of the arts and humanities disciplines that really need to be on campus, they'll find a way to make that work. Now, I have no idea is the truthful answer to your question, but I really hope not. This is not, there's a reason that nobody tries to do this. I went looking for places that offer online physics classes, and the only ones that I could find that looked at all reasonable were designed for Air Force pilots. And, you know, Air Force pilots are a very different group than you guys or any group of students I've ever dealt with. So anyway, and, you know, I'm not entirely sure it works effectively for the Air Force pilots either.
Thank you.
All right. So I was also going to mention, you should be getting an email in the next couple of days from me that just asks you to take a really quick survey. This is just me trying to gauge any sort of feedback on the effectiveness of what we're trying to do here. You know, it's your chance to let me know that everything sucks, which I know, I agree. But if you want to, but this will help me get some idea of maybe which parts are better or worse, at least for helping you guys learn the material. So that should be coming in your email. Okay, so here's our poll to start off the day. So this is actually a comment from the perusal reading. So the question was, does conservation of momentum mean that momentum is never created nor destroyed, but rather transferred between one system and another system? Okay, I'll give you another 10 seconds here. Okay, going once, twice. Sold. Okay, so if we share the results here, you'll see that most of you said A, yes, That's how I would answer this question. That yes, conservation of momentum means that momentum is never created or destroyed. It can only be transferred. And this is actually one of the really nice things about momentum is that because it can never be, you can't ever make any new momentum or get rid of any existing momentum. You can use it to think about things where talking about the forces on objects might be very difficult to calculate. But the momentum before and after, because it couldn't be created or destroyed, can be tracked. So really, that's the idea here, is that conservation of momentum is this idea that momentum can't ever be created or destroyed. And as we'll show here in a minute, it actually comes from Newton's laws. So here's another question to play with. Let me relaunch the poll. Maybe. There we go. All right, so you've got a billiard ball. It's hit and it collides with two other billiard balls on a pool table, and the other two billiard balls were initially at rest. All three balls have the same mass. Immediately after the collision, which of these is not a possible outcome? And I don't know what you do for E, because there's no E on my polling question. But if you really feel it's E, I'll give you a chance to defend yourself.
I can't see a poll if it's up.
Okay, it doesn't look like anybody can see the poll. Let me try it and relaunch it again. Okay, how about now?
I can see it.
There we go.
Great.
There's no E option though.
Yeah. So if you wanna go with E, then I'll just don't vote, and I'll give you a chance to defend yourself here in a minute. Okay, I'll give you another 30 seconds. All right, going once, twice. Sold. All right, E's. Who wants to defend E? Vote E. Potentially think about E. All right, apparently we've rejected E. Most people said D, and D is actually the correct answer here. All three of the balls are not moving is not a possible outcome. And the reason for that is simply that momentum has to be conserved. So if there's some momentum initially, we can't end up with a scenario where there's no momentum anywhere, right? So the other ones are all possible. A, B, and C are all possible. You can arrange the collision in such a way that all three of the balls end up moving, or one of the balls is moving, or two of the balls are moving. But you can't work this out so that none of the balls are moving, because none of the balls moving has no momentum, right? So remember, we can trade momentum around, but we can't ever get rid of it. So let me show you where that comes from. So if I stop my share over here and I switch to that. All right. So we all remember way back when life was simple and things were, in person. We talked about Newton's laws, right? So one of Newton's laws is that the force from one object on another object is equal to the negative force from the second object on the first. So let's imagine that. Let's imagine I have two objects here, right? And they're touching. So object one, so here's one and here's two. Object one is exerting a force on object two. So that's the force from object one on object two. That means that object two has to be exerting an equal force in the opposite direction on object one, right? And this whole thing is Newton's third law, right? This equal and opposite forces on different objects in an interaction, right? Forces are all about interactions. And Newton's third law says that anytime you have an interaction, it has to be such that each object gets the same amount of force, but in opposite directions, okay? Now, if we remember, last time we talked about how Newton actually wrote his second law. Newton wrote his second law as the sum of the forces on an object is equal to the time rate of change of the momentum of that object, okay? So for any object, if I apply a force to it, what that force does is it changes the momentum of the object. So what I can do is I can come up here and look and examine this system in terms of the time rate of change of momentum. There's only one force acting on each object, right? So I could write F12, that's the force on object 2 from object 1, right, is equal to the time rate of change of object 2. And I could write that the force from object 2 on object 1 is equal to the time rate of change of the momentum of object 1. Now I can do something a little interesting here. I'm going to add these two equations together. And I can do that because I can add the same thing to both sides of the equation. So I can add whatever I want, right? I can add force of object from object 2 on object 1 to this equation, and I can add the time rate of change of momentum of object 1 to this side of this equation. And what I get is something that's going to look like F12 plus F21 equals the time rate of change of the momentum of object 2 plus the time rate of change of the momentum of object 1. Okay, this term here, I can look up here at my Newton's third law, right? Newton's third law says that all F12 is negative F21. So let me come over here. So if I plug that in, right, what I get is negative F21 plus F21 equals, and I'm going to do something fun down here. Okay, I've got two time derivatives. If you remember, if I take the time derivative of the sum of two functions, that's the same thing as the time derivative of each function added together. So I can rewrite this as the time derivative of momentum of object 1 plus the momentum of object 2, right? I can just essentially factor out the derivative. Okay, well, this is 0, right? Because I've got negative a thing plus a thing. That's just 0 equals the time rate of change of the two momenta. This is conservation of momentum. This statement right here says that in any interaction, right? Any interaction between two objects, there is no change with respect to time in their momentum, right? And if the time derivative is 0, that means these things have to be constant. This is conservation of momentum expressed mathematically. If the time derivative of something is constant or 0, then that something has to be constant in time. Now you'll notice I didn't assume anything about the forces here, right? I didn't assume that they were conservative forces. I didn't assume they were even, you know, the only forces acting on an object, right? I could very easily draw another thing over here and show that this same thing works with the third object. But I did assume that there were no forces coming from outside of our system. What do I mean by system? I mean the objects we're considering, okay? So I can get momentum from another object, right? But I can't ever, all I'm doing is trading momentum, right? If the momentum of object 1 goes up, the momentum of object 2 has to go down. If the momentum of object 2 goes up, the momentum of object 1 has to go down. If object 2 shoots off to the left, then object 1 has to go to the right, an equal amount of momentum, because these vector sums always have to add up to a constant, okay? So Newton's third law is really just a statement of conservation of momentum, okay? That in every interaction between any two objects, the total amount of momentum is conserved. Okay, so let's talk about this a little bit, because this is not necessarily the most intuitive thing. So let me come over and we'll see if this works. Okay, there's me, but let's see, actually I want this one. There we go. Nope, that's not gonna work. I need the other one. Okay, I'm gonna point it up a little bit and I'm going to see if I can do this without messing up my headphones. Okay, so here's what I want to do. I want to show you an interaction. Well, hold on. I'm going to have to mess up my headphones. Okay, can you still hear me? Yes?
Yeah.
Great.
I'm designed to wait in standby mode until I'm activated, like when you say, "Hey Google."
That's really nice. My phone decided I was talking to it. Okay, so here is my experiment, right? What's the momentum of my pen right now?
Nothing.
0,
Zero.
right? Not moving.
0.
Okay, and I'm going to drop it and catch it. Well, I didn't catch it, but you got the idea. What was the momentum of the pen right before it hit my hand? Not 0, right? It was moving. It was moving downward. So 0 momentum, some momentum. So what happens? Where did that momentum come from?
Gravity?
Gravity. Okay, gravity is a force, right? So gravity is an interaction between the pen and what?
The Earth.
The earth, which means that the momentum the pen had right before it hit my hand came from where? Everywhere, right? The earth. It came from the whole planet. This pen stole a little bit of momentum from the earth, okay? So, again, if I drop the pen, no momentum, momentum. That momentum has to come from somewhere. And where it came from was the ground, right? The earth actually lost a little bit of momentum, okay? Now, let's try to make sense of that. Because we've been talking about this momentum stuff in terms of a system, right? So this becomes important, how we define a system. All right, let me get my headphones back. Okay, so our system is the important point here. When we talk about dropping the pen, right? The pen drops. It gains momentum as it drops, right? Because it's moving faster and faster, and its mass isn't changing. That momentum is coming from somewhere, because that's what conservation of momentum means. In this case, there's only one place it could come from, and that's the rest of the world, right? Now, that means that if I think of this system at rest initially, when I let it go, the rest of the world, because the pen gets some downward momentum, right? So the momentum's pointed down. That means the rest of the world had to have that same amount of momentum pointed up, which is weird to think about, that dropping a pen made the entire planet move upwards. But here's the way it works. How fast did the planet have to move upward to have the same amount of momentum as this pen moving down? Well, you can run the numbers, but the answer is something like 10 to the negative 26 meters per second. Okay? That's a 0.25 zeros and a 1 meters per second. Okay? For reference, an atom is about 10 to the negative 10 meters in size. So you're talking about something, a motion that is smaller than an atom is to us to an atom, right? So take the scale between you and an atom, go down that far again past atoms, and you're talking about the amount of momentum this pen had to cause the earth to have, or the amount of velocity, because the earth is huge, okay? So when we think about conservation of momentum, the really crucial thing is to identify a system, okay? Identify all of the things that are interacting, all of the forces on an object. Momentum will be conserved for as long as between objects that you're thinking about, okay? It will not be conserved if you're not thinking about the object. So when we think about this pen falling, we usually don't think about the planet moving with it, right? We just think about the pen moving. So it looks like the pen got momentum from nowhere. It didn't. It got momentum from a really, really, really big bucket of momentum that was available to it, right? The earth. The earth has a lot of momentum. It didn't mind sharing a little teeny bit with a pen, okay? So let's look at this in the context that we showed for the video for video experiment number 3. So if you watch this thing, right, you guys have all played with the Newton's cradle before. You pull back one ball, you let it go, and it just clicks back and forth, right? You could watch that all day. This is why, like, business people have these on their desks. Okay, so when you think about this, if we want to talk about conservation of momentum, we need to remember that we have to include the whole system, okay? So the thing I want you to think about here for a minute, and then I'm going to give you a chance to respond, is when we talk about conservation of momentum, which interactions here are going to conserve the momentum of these metal balls? And which interactions are not going to conserve the momentum of these metal balls? So I'll give you a second to think about that, okay? I'll say that one more time. Which interactions, which forces, right, that are acting on these 5 metal balls are going to conserve the momentum of these 5 metal balls? And which forces acting on them are not going to conserve their momentum? So give it a second, ponder that, and we'll come back and talk about it. I'm just going to leave this playing because it's fun. All right, so let's start with which interactions do conserve the momentum of those 5 metal balls. What interactions, what forces do that?
When they collide with each other.
Okay, so what kind of force is that? If we play this thing, so let's think about the instant when that first ball hits the second ball. Okay, what kind of a force is that? If I were to draw the free body diagram for that first ball, the moment it's hitting the second ball, because remember, collisions might be really short, but they do take some amount of time. What would you call that force?
Like a push?
A push. Yeah. It's like a normal force, right? It's a contact force. It's simply, if we were to zoom in on this thing, right? We zoomed way in right as those two things are hitting each other, right? So we came down here and we looked right there when they touch. What we'd see is that this ball, the first ball's electrons, don't like the second ball's electrons. And so when they get close to each other, they push away from each other, right? In this class, we're just going to call that a contact force, okay? So there's a contact force. So I forgot who said, was it Davey that said it? We'll give Davey credit. I don't know if it was him or not. Said that that one is going to conserve the momentum of these 5 balls here. Does anybody disagree? Does anybody agree? All right, give me a thumbs up if you agree. All right. I see a lot of thumbs up. Okay, that's good. We'll take that. Okay, so what that means is we've got a interaction between objects, right? So if we talk about the force here, the force on ball number 1 is coming from ball number 2 and vice versa. So you're right, that conserves the momentum of those two balls, right? Because that interaction can only trade momentum. It can give some of the momentum from ball number 1 to ball number 2, or vice versa, right? Okay, so what forces, any other forces that would conserve the momentum of these objects? Okay, how about forces that would not conserve the momentum of these objects?
Air resistance.
Air resistance. That's absolutely true. That would conserve the momentum of the balls and the air, right? But we have no way of seeing the momentum of the air. Well, we don't. There are ways to do that, but we don't. Okay, so air resistance definitely would. That's why it eventually stops. Part of why it eventually stops, right? If you leave that thing clicking forever, it will eventually stop. And that's because eventually all of the momentum will have left those those 5 balls, and will be somewhere else, like the air, right? Okay, where does it go from the air? If I have an object moving, right, and there's air resistance on it backwards, that means there's some momentum, some of the forward momentum is being transferred into the air. Well, where does it go from there?
Sound.
It can go a lot of places. It can go into sound. It can go, so sound waves can carry momentum. Okay, we won't get into that in this class, but it's true. Okay, it turns out what it does is it spreads out. Is if you have air moving this way, right? You have air moving across the screen. What it's going to do is it's going to make the air next to it move a little bit with it, and it's going to share its momentum. And so pretty soon, instead of having one little bit of air moving really fast, you have a whole bunch of air moving really slow. Okay? Okay, so not air resistance. What else doesn't conserve the momentum of these 5 objects?
The heat created by the balls contacting each other.
Okay, that one actually does. It doesn't
True,
conserve energy, but it does conserve momentum. The interaction between the balls does conserve momentum. But that's a good
Yeah,
thought.
it's still in the system.
Okay, so there's 2 more. If I were drawing a free body diagram of, let's look at this ball right here. Okay, what forces are acting on this ball right now? The one that's swinging out to the side.
Gravity and tension.
Gravity and tension. Are either of those going to conserve the momentum of these 5 balls? Conservation of momentum only works when you're talking about both of the objects that are involved in the force, right? Because forces always take 2 objects, right? So this force, the tension force, right? That force is going to conserve momentum. It's going to transfer momentum between the ball and the top of this Newton's cradle, right? And that's going to transfer it to the sides, and that's going to transfer it to the table, and that's going to transfer it to the carpet, and that's going to, right? It can go a lot of places. So this isn't something we usually think about, but it absolutely is transferring momentum. And how do I know it's transferring momentum? Well, let me step back just a hair here. Okay, right there. Okay, So if I right here, right, this ball is coming in, it's going to hit this guy, which is going to hit that guy, that guy, that guy. Right now, how much vertical momentum does this ball have? The one on the end?
None.
None. So, but after it gets hit, right, if I step forward just a smidge, now it's got some vertical momentum, right? Because it's going to go up. It's going to swing up this way. So where did that momentum come from? Well, the only force that could make it move upward is this tension in the string. So where did it get that momentum? Well, it stole it from the structure and the table and the floor and the earth. Okay? So the tension force conserves momentum, but it's taking it out of the system that we care about, right? Because the system that we care about are these 5 balls. Okay, there was one other force we talked about, and that's gravity. Gravity also is going to add or subtract momentum from the system of these 5 balls. How do I know that? Well, let's go back to the beginning here. Okay, I'm going to pull the thing back. Oh, no, dang it, don't do that. When I pulled the thing back, right before I let it go, how much momentum did the system have? 0, right? Nothing's moving. Right? But once I let it go, that ball got some momentum, right? If we watch this thing again here. Oh, come on, thing. Well, apparently Newton's cradle is only viewable like 18 times. Oh, there it goes. Okay, that may have been me, not YouTube. Sorry about that. Okay, so right before I let it go, the system has no momentum. But then once I let it go, the system gets momentum, right? That ball accelerates downward along that arc until it hits the next one. Okay? So the key when we talk about conservation of momentum is identifying your system. Okay? Because inside of that system, any interaction can only trade momentum around. But any force coming from outside of your system can change the momentum of your system. You can get momentum from somewhere else that we're not tracking, not talking about. And the Newton's cradle is a great example of why. Because the momentum that we're getting from other sources is coming from essentially the ground, right? Through this fact that this Newton's cradle is stacked on top of a table, which is stacked on top of my floor, which is stacked on top of the ground. And it's getting momentum and losing momentum from the earth itself. Both of those are impossible to track. So we don't even try. We just say, okay, that we only worry about the momentum that we can track. Now, here's the really nice thing. It turns out that the reason you make a Newton's cradle out of steel balls is because you want those interactions, those forces to occur on really short time scales. Okay? And if you remember, we talked about last time, when collisions are short, that makes the forces really big. So for the brief moment that this ball number 1 is hitting ball number 2, or ball number 2 is hitting ball number 3, or ball number 3 is hitting 4 or 5, that force is way bigger than any other force acting on that ball. So we can assume it approximately conserves momentum. Okay. Okay. Questions? How are we feeling?
Eh,
Eh? Eh. Okay. Let's do some practice problems. Okay, I'm gonna try something and we'll see how it works. I'm trying new technology today. So
I don't know if it's the same for others, but you've stopped moving on my screen.
my
I think
my
it's your
internet
internet.
is my internet dying painfully. I'm gonna take that as a yes because nobody's
Yeah,
talking
there's
to me. Oh goodness. Okay. Well then maybe I won't try new things.